it on.
Yeah, it's unmute.
Now it's on mute, yeah.
Okay, unmute it. Perfect. Hi everyone. We are going to begin the next talk from Floris about teaming greenlets using Eventlet. Let's. Sorry. Okay. Let's begin.
Okay, hello everyone. Using greenlets and eventlets. First of all, I'd like to ask how many of you have went to the green concurrency using greenlets talk earlier today?
Could you speak up a little, please? Yeah, please.
Yeah, I'll try.
Thank you.
If you went to the talk earlier today to the concurrency using greenlets talk, that was kind of very complimentary, I think. He explained a lot of the concepts as well that I go through maybe a little bit faster. Mainly the talk is I'm going to go through a simple example of some networking code and go through like the stages you try to make it deal with many clients, etc. I'll then go into more detail about what greenlets are, which is the underlying technology that makes it work, and then how Eventlet builds on top of that to help you write networking code. I'll then detail a bit more about the pros and cons of monkey patching, what you can do to avoid that, and then also talk about using multiple threads as well, which in my opinion has its advantages sometimes. So Eventlet, in case you don't know, it's a library to help you with writing concurrent networking code. That doesn't mean parallel. Concurrent means that you can handle multiple clients at the same time, really, but not really parallel. So you can still be sequential. The advantages of something like Eventlet or Gevent is in the same kind of area. The advantage of that is that you can write your code in a very natural way, just like the same way as you'd write it if you were writing blocking code. And yeah, it implicitly does dispatch and behind. I'll get to that behind the scenes for you to make all of that work in a scalable way. I've been using Eventlet since about 2010, and one of the weird things we kind of did was we had an existing application that was using multi-threading, and we needed to handle lots of clients in that. So we wanted to use something greenlet based in that, and we ended up picking Eventlet. And that's kind of a different approach as most of the examples give you, because most of the time, if you go to something greenlet based, it's kind of you write the entire application from the start to use that, rather than actually mixing and matching threads and greenlets. The example I'll be running through is basically a very simple echo server. You probably all know this. So you just send any string to the echo server, and it just replies. It just sends content straight back. There's even RFC for this. It's like the most brief and sloppy written RFC I think you can ever read. But it's just for testing applications really. But it's a good example. Client looks very simple. So you just create your socket, you connect to the server. And you send some string, you then listen, and it should echo that back to you. At the end, you close the socket. So when you're writing a single client like this, it's very straightforward. There's no problem with where the blocking calls, where you do send and receive, because you have no real issues there. When you'd like to write a server for that, a first go at writing the server for this would probably be something like this, which is you create the socket again. This time it's a server socket, so you bind it to listen to an address. So the tuple that you pass in is like an empty string. It means listen on all interfaces of your server or whatever device you got. and listen on port 7. That's the standard port for echo service. Then you need to call listen on it, so your socket will actually be listening. And then where you do the accept call, this is kind of, the server will then basically block at that point, and it will wait until the client connects. Once the client is connected, you get the client, which is just another socket returns. Then the server can start listening for data, receives a bunch of data, and then sends it back and reads the next bit of data. Once the client has disconnected, the receive will receive an empty string back, and you go out of while loop, close the socket, and it will go back to accepting the next client. The obvious problem with that is, very obvious, is you're only handling one client at a time. So that doesn't really scale very well. Also, as a side note, kind of, this is not how you write the service, because this hard-coded stuff, you're not handling IPv6, and you can easily write it to do both things. Anyway, so yeah, it's just a quick example to make it work. The one of the obvious things that usually, the next thing that you go and look at is like threading, because that's kind of the standard solution for handling multiple things at the same time. The flow you go through is very similar. You create your socket, bind, listen, and then when accepting a client, instead of just handling a client, you create a new thread to handle that client. So you start this helper function called handle client in a new thread, and there you do exactly the same. You receive data, you send it back until the connection is closed, and then you close the connection. This works very well. Creating threads is something that the operating system is very good at. Managing threads is very good at as well. There's been tons of research into scheduling and all that, and the operating system will make sure that all your threads will get you run and at the time they need to, etc. So if this kind of solves your problem, then that's a good thing to stay at. But that's, for those that went to the talk this morning, they will know that this kind of starts to break down when you have to handle a lot more clients than just a couple of hundred. There is a certain overhead associated with threads, both in memory as well as in time to switch from one thread to another. And when you got in general, you can have a lot more file descriptors, which is what sockets are, to communicate. You can have a lot more file descriptors than threads in your operating system. And so if you need to handle lots and lots of clients at the same time, the threaded methods start to kind of break down, and that's where you need to look at other solutions. Again, the generic answer to that is kind of, there's a system called select. Select is a system call that you give it a bunch of sockets you want to do stuff on, either listen or either read from or write to, and the system call will return you those sockets that you can do those operations on. So that means you can juggle lots of sockets at the same time without ever having to block on one. Running through it, so the beginning is kind of the same. You create your socket, bind, listen, and then select. Kind of the API takes a list of sockets you want to read from and a list of sockets you want to write to, and then it takes a third list, which is something like exceptional conditions, but that's not very important. You should never really need that. And in return, it returns you a list of sockets that are ready to read and a list of sockets that are ready to write. So when you call select, if there's nothing happening, so you just start your application, there's no client connecting, that will be a blocking call, and your application will just sit there waiting until something happens. Once a client connects, select will return, and the service socket that you got will be listed as in the list of the sockets that are readable. So in that case, you go through to the if statement, and you just accept the new client, and you prepare the lists for the next select call again. So you put the sockets you want to read from and sockets you want to write to into the select call. So in this case, the client socket is one that you both want to read and write to, because you will have to echo the information back. And obviously, you still want to be able to accept new clients. So you want to so you want to still read from the server socket as well. So next time around, you sit in the select loop, say no other clients connect. So the next time around select returns, you should have your client socket both readable and writable normally. If the client has actually sent data across to you, then it will be readable. So select will return, and basically you then go through the client, receive the data, you check whether the client's closed the socket. If not, you send data back. When it's closed the socket, you remove your client. I actually forgot to close the client socket there as well, which is not a terrible mistake. But once Python's garbage collection will clean up the socket, it will be closed automatically. But this is quite involved, because you have to juggle around those socket objects, and it gets even worse when this time around we could write it in a way without needing to keep state about one socket. But if you have to keep state for a socket, you have to, if you have a stateful protocol on your socket or something, you have to keep track of where you are in each socket, and you have to store all the data, juggle it around, and it all gets a little bit quite quickly gets rather complicated to keep track of what's going on. So, sure.
That's two lines. Is that source socks or sub socks that
So the last line here. This one.
Source sock.
Oh, that should be SRV. Sorry, that's not a mistake. Yeah, that's SRV socket. Apologies. Okay. So instead of having to go through all of that, so the previous slide was all running in one thread. So there's no multiple threading. Instead of having to go through all of that, select system calls, etc., you can write exactly the same, very, very similar to what the threaded solution looked like, which is, this looks almost exactly the same, apart from where you create the thread. You're now spawning a new greenlet, really, and the handler of the greenlet is exactly the same. And what this does is, so in each blocking operation, basically, instead of blocking, the eventlet will allow the other greenlets that already exist to run as well. So it's still single threaded, and everything will run linearly, but Eventlet will make sure that you can handle that multiple clients are handled at the same time, and instead of when one client is waiting to receive some more data, it will switch back to another greenlet, and it will use that one and it will let that one carry on. So that's basically what Eventlet allows you to do, and that's how you can scale without avoiding threads managed by the operating system, and therefore handle a lot more clients. So kind of taking a step back, really, looking at greenlets. So greenlets came about from Stackless Python. Stackless Python is a project that's been around for many years, actually, and it basically allows you for something very similar way of working, but Stackless Python is an entire fork of the Python interpreter, and Greenlet kind of grew out of that, and it's when the main authors figured out how to basically take that functionality of switching user-land stacks out in just an extension module in CPython. The other, it's currently still actively maintained, and it's actually supported on a lot of architectures as well. So I think PowerPC and Spark and I think ARM are all supported, as well as classic x86 and MD64, etc. So it's a well-maintained kind of small little module, but and it's also like PyPy supports it as well, which is very nice. They even in one of their latest releases they started to include it in the JIT, so it's optimized there too. The downside of it is that on its own it's not very easy to use, and that's why generally you will not be using them directly, these greenlets directly, but you'll be using them in a framework. This is an example of like the API of what one greenlet does. So just like in threads, if you start your application, you're in the main thread kind of thing, and you don't necessarily need to create new threads. But if you create more threads, you have your main thread and you have your other threads. Just like that in the greenlet world, you always have, when you start, you're just in the main greenlet. If you then like create a new greenlet, you again need to give it a function body as what the greenlet will actually run, and then you can manually. Greenlet just allows you to manually switch between these different lightweight threads almost. But everything happens linear. So because all of this is running within one thread. So in this case, it's, you never, if you were to try to do this with threads, you might not always be guaranteed the same order of your results. In this case, you will always be guaranteed the same order of results. So what happens when one greenlet tries to switch to another? It's trying to, so if you know in the in the memory of your process, you have your stack where you got all your function calls and frames, etc., with the parameters of your function calls, etc. So when a greenlet switches to another one, what the extension module actually does under the hood is it reads what's on the stack and it saves it away on the heap. And the heap is like where you normally allocate your memory. So if you've ever done C programming and you malloc something, that's the heap. So it just takes whatever is on your stack and it saves this onto the heap. And then you just continue executing in your new greenlet. And then when you want to switch back, you basically, again, you take your stack from your current greenlet, you save it in a new place on the heap, and you take the previous stack data that you saved away earlier, you put it back onto the stack, and then the reason. So the extension module then needs to do a little bit of assembly code to change the registers that point to your that point to the stack pointer and the frame pointer. So once you've adjusted those stack pointers to point to where your new stack now is, which you copied another one back in, then you just let stuff run on as normal, and you basically very lightly switched between these two different threads of execution, so that is a lot lighter than a full context switch if you use a real kernel thread. So that's why you have less memory overhead, and it's also a little bit quicker as well. So that's what greenlets allow you to do under the hood, really. Yeah, and then so they got a little API inside that. But normally you should always be kind of hidden. That should always be kind of hidden to you. Eventlet and similar systems like gevent will have a hub, they generally call it. And this hub is in control of running the greenlets for you, so you don't have to do this switching to one and switching back, etc. And the hub is basically, you remember when we had the slide with the select DOM, where you waited until the socket was ready to do something on. That is essentially what the hub does. The hub is there as an I/O loop, so it looks at all the sockets you want to do operations on, and when one of those operations is possible, it will give that socket and pass it on to the greenlet that wants to use that socket, and then let that greenlet run. When that greenlet is done running, which is basically because it reaches another blocking operation, so instead of that greenlet will block, instead of that it will pass control back to the hub, and the hub will then do that again and find the next socket where operation needs to happen on. That's essentially what Eventlet does, and it allows you to write this code in what looks to you like a blocking manner, but by using those greenlets, it will switch to other things that can do work. Another nice thing of the hub is that it will select the best kind of method. So I showed select earlier because select is kind of the common denominator. It works on all platforms. Problem with select is it's kind of very inefficient because you have to create all these lists, and these lists always get copied around, and that just takes a lot of time. So people over time have improved the kernel interfaces to make this work in better ways. I think Polar and ePolar Linux interfaces, KQ is a BSD one. So the hub will kind of select you the best kind of way of doing that I/O, so it kind of happens quicker. As we already saw, you can spawn greenlets using Eventlet.spawn, and that doesn't create a new thread. So it just kind of creates this new greenlet with a function body. So you pass in a function body into spawn, and it creates this new greenlet. But the thing to realize actually is, so when you create your new greenlet, you get your greenlet object kind of, which is actually Eventlet kind of wraps that slightly into an API that allows you to do a little bit more than just greenlets. They call them green threads. I tend to use both names together, so that's not really entirely correct. But so when you've actually spawned your greenlet, it hasn't actually started executing this yet. So you're still running in your single threads until you do something that is blocking. Something that is blocking, Eventlet.sleep is kind of the blocking operation for the sleep operation for Eventlet, just like time.sleep is in a normal thread. But sleep of 0 is kind of a small trick to yield to the hub. It's kind of saying, I know I'm taking up CPU at the moment, and instead of I don't really have to block or wait on anything to happen, but instead of keeping the CPU to myself, you kind of pass control to the hub, and the hub will then have a chance to run other greenlets that do something. So that's what's happening here. So you just pass control to the hub, which then has time to start running this function. And then the other nice thing really it gives you is it adds kind of a wait method onto your greenlet. So you can wait until a greenlet has finished, and you can get the return value of the function body. If your function body, sorry?
A certain rule of B is false. Where does the B come from?
Sorry, say again? Speak.
Should this be a certain rule of
G.
G?
Yes, that should be G. I do apologize.
Return equals 42.
So sorry, return equals 42. Are you asking where that comes from?
Yeah, what does it mean?
I'm just this is just an example of a function body basically. So
I'll return 42 or return equals 42.
Oh yeah, that shouldn't be equals. Yes, you're right in that. All right, so yes, return value should be return value. All right. So you can wait until a certain greenlet is finished as well. If a greenlet, instead of like in this case, it would have raised an exception. instead of getting the result, the exception, when you call wait, the exception will actually be raised as it came out of the wait call. So that's the abstraction that Eventlet gives you there. Another common thing to use in Eventlet is this pool kind of thing. So in this case, I create an Eventlet socket rather than a normal socket. And do everything the same, but instead of spawning these client handlers directly, by putting them in a pool, you can sort of restrict the resources. And a reason you might want to do this is because if you just accept every connection, you can exhaust your application of all file descriptors or something like that. And you may want, you may want to look at, still needs file descriptors for other areas of your application, etc. So that's kind of a common API in there. The common way of doing things, what's always said, is like using this monkey patch kind of thing. The thing is, that's really not. I don't think that's a very good way of using your greenlets, because it kind of you're depending on a lot of things there. You want, if you do monkey patch, so monkey patch basically will take the Eventlet implementation of socket that uses this hub, etc., and it will put it in place of the implementation in the standard library. So if you do import socket, you'll actually get the socket implementation of Eventlet, and it will do this for the other libraries as well, like threading, etc. So in that case, when you're doing creating a new thread, you won't actually be creating a new thread. You'll be spawning a new greenlet. But that's because you're trying to rejig the standard library basically and make it behave differently. You have to do this early on in your application, and then you get into trouble where import order matters, stuff that you sort of end up doing that at import time, which is never really that good.
Can switch off the cell phone because there's obviously something that's interfering with the camera and the audio. That's not only to silent the ring, but really switch it off.
Okay. So yeah, monkey patching is a kind of, to me, I don't think it's very good engineering. It kind of hides what you're doing as well, and eventually, in my experience, eventually abstractions will always kind of end up leaking when you're debugging. Things will kind of look different, etc. So I don't really, I'm not really a big fan of monkey patching. Instead, I think it's perfectly, and in Eventlet, it's perfectly possible to just import selective things as green modules, basically. And the way Eventlet does that is it allows you, it has basically the entire standard library available under Eventlet. Well, not the entire standard library, but the parts of the standard library that are using blocking operations that wouldn't have to be monkey patched. So the socket module will be under event.green.socket. You have that available. The threading library will be under there, the thread library, etc. So anything that, and that allows you to basically, you can actually import both Eventlet socket module and the real socket module, and you can use them at the same time as well. And you'd also, with the, so that works for the standard library, and then for third-party modules, etc. If you have to do that, you need to use this import patched call. Import patched will import third-party modules, but the thing to look out there is that it only works on pure Python modules, because if you've got an extension module that's using a socket below the hood itself, there's no way Eventlet can kind of stop that from happening. So import patched is kind of the same restriction as with monkey patching. You only can do that on pure Python modules. Another thing to currently look out for is when you do import patched on a package, like the example here, requests is a package. That works fine. You can import requests like that, and you'll be able to use it fine in a concurrent way in a greenlet world. Unfortunately, if you then try to import it again as a normal non-patched or non-green version as well, the current implementation of the patcher in Eventlet doesn't actually work. Will actually subtly break. That's something unfortunate, but we're also aware of that, and hopefully that should be fixed not too long in the future. So that allows you to kind of build a world where you have both Eventlet kind of modules or code and code that's actually really blocking. Another thing to deal with blocking calls is Eventlet comes with a tpool module, which is like a thread pool. If you have to do something that really is blocking, a common example is something like a database that only provides, or you've got an extension module that uses a blocking API. You can't do anything about that. In that case, you kind of have to run it in a thread pool, and the way the thread pool is kind of set up so that Eventlet can execute a function in a different thread. So that thread is then allowed to block. By default, you've got something like 20 threads or so. So that those threads can then block, and then whenever they finished executing, Eventlet will give you the result back, and your main Eventlet application will not suffer blocking, so you'll be able to keep doing your I/O as normal. The things to look out for there is that you can't really, you want to avoid starting an Eventlet hub in one of those threads as well. And also you want to keep the code you dispatch to a different thread to an absolute minimum. At the moment, there is, if you end up using a synchronization object that's made for Eventlet, like you created a semaphore or lock or something like that, and you end up passing that into another thread, things will actually, if another thread tries to use that Eventlet synchronization object, things will break, and that is actually something that happens with the logging module, because the logging module under the hood does uses some locks, and if you do that will break. This is something again that there's actually being worked on, and that will improve as well. So that's kind of safe to do as well. The example I give here with get adder info, that's kind of a random example. The reason the IPv6 kind of works fine in Eventlet, but address resolution or IPv6 address resolution in Eventlet isn't complete yet. So that's why I use that as an example. Right. So you got. So yeah, I think if you understand how greenlets work, so greenlets handle, and the hub handles all the greenlets to do I/O, etc. But the main issue, well, the main difference with real threads there is that on greenlets you will be, everything happens sequentially, and if you need to do lots of CPU things or something like that, you are restricted until your code actually yields back to the hub. And sometimes that's the advantage of real threads managed by the operating system, because the operating system has a scheduler. Again, you know, that's been very optimized for a long time, and the scheduler will kind of juggle the threads around so everyone gets a fair chance. And in the blocking in the Eventlet world, you're kind of responsible for that yourself. So that's why I don't think you should always restrict your design to this monkey patching world where everything is just a single thread in your process and everything runs with and everything runs with that in that one thread. And if so, I think if you end up doing it's quite all right to use multiple threads as well. You can even use multiple threads with Eventlet hubs, etc. You might want to run 2 Eventlet hubs for some reason, or But the problem is basically communicating between those threads. You still need to be able to do that. So the standard library queue module is, you should always kind of, message passing is always better than trying to do stuff with locking, etc. So generally, when you need to pass data around between threads, you want to use the queue module. The issue with that is that when you use the queue module, it works fine between two real threads. But if you've got one or both of those threads that have an Eventlet hub running in them, when you're trying to the queue module or implementation actually under the hood uses a lock, and the lock is being the lock eventually it's a lock implementation provided by the OS. So once you're blocking on a lock in the queue module, like you're trying to put an extra item on the queue while it's full or something like that. Once you lock that, you lock the entire thread up, and if you end up locking up the thread with your Eventlet hub, that means none of your other greenlets are going to be running anymore. If none of your greenlets are running, you're not handling all the I/O to your clients, etc. So that's something you want to avoid. Likewise, there's greenlet comes with its own queue implementation, but this problem is kind of the same as I mentioned in the T-pool module. When it doesn't work across threads, it's the default queue implementation in Eventlet will only work to pass items between different greenlets of the same thread. So one solution that we're currently working on as well is this cross-thread module, which gives you basically locks and all those things, but essentially the thing you really care about is a queue that works from passing data from one that can safely pass data from one thread, whether it is in a running Eventlet hub or not, to another thread. Another way of probably approaching that is using ZeroMQ. I have to say I haven't used ZeroMQ myself yet, but ZeroMQ is supported by Eventlet, so there is and ZeroMQ. So if you can use ZeroMQ from both Eventlet and from your real threads, ZeroMQ should be able to you should be able to do message passing between all those as well in a safe way without blocking. However, if you that's fine if you're already using ZeroMQ, but it's quite a big overhead to just introduce ZeroMQ if you haven't if you weren't using it yet. So using there really is nothing different about using the queue kind of thing from the cross-thread kind of module. You just have producers, consumers just the same way. The main things to worry about is you kind of need to be aware from you need to look out for what you're working on. You need to know if in general you don't want to same as in the T-pool module really. You don't want to accidentally start a hub in a place where you didn't want to start a hub or etc. because then things might start to behave slightly different. Yeah, so that's kind of Xthread. It's very like usage is very easy. Inside it, like it's quite a little bit. It's quite a tricky implementation actually inside it. Basically, and this sort of extra detail. So when you're trying to block in a greenlet that has a running hub, etc., instead of blocking, you always switch to the hub. So that's what the implementation has to do. And the main problem is you can never really acquire a real lock, and that makes coordinating with another real thread that actually has to use a real lock quite tricky because there's a lot of race conditions there. Likewise, when you want to unblock that blocked greenlet, then you have to schedule the switch back to the greenlet in the hub. Fine for a greenlet in the same hub, that's easy enough to do. If you're doing it from another thread, you kind of have to use, generally, the way to do that is it sets up a pipe, generally, where you just have a socket where you can write something up. Because if the hub that you're trying to signal if that was in the select call or the equivalent, and it was nothing was happening to it, it didn't have any reason to wake up in the next 60 seconds. So it would just sit there 60 seconds before you would unlock your greenlet. So that's why you have to be able to do that. In threads, it's quite. So yeah, there was locking and unlocking. So in threads, it's quite a little bit more straightforward. You actually, when you want to block a real thread, you just use a lock that the thread tries to acquire. Unlocking that is safe to do from a greenlet, so that's quite straightforward enough. So that's kind of a little bit of a very, very short way of introduction to how this communication can actually happen between different threads. So what I said earlier, you kind of want to watch out. You always want to kind of know which environment you're working in. If you're working, whether you're working in a greened environment that's running on an Eventlet hub, or whether you're working on a real thread. If you start calling Eventlet calls in the real one, you're gonna start a new hub in that thread. Might not have been what you wanted. Other stuff might start to behave differently. So keep track of which environment you're working in. Yeah, the default implementations of like Eventlet comes with semaphore locks and messages, events, all that stuff. So by default, at the moment anyway, they're not cross-thread aware, so you can't use the Eventlet things to signal between different threads. So if Eventlet is so there is bugs for some of these issues, and the Xthread module is likely to be merged, probably slightly different as it is now. But the main issue is that that example I gave from T-Pool, if you have a logging call in a different thread, that's kind of seen as a big issue. So the idea is to try and merge the Xthread code to solve that issue. Currently, Eventlet is only Python 2.7 as well. There is again, we're hoping to port it to Python 3 as well, so we will eventually get there. And then, yeah, the IPv6 stuff is it's mostly alright. It's just address resolution, really. And that was mostly it. So the most important points, really, I think, is like monkey patching is not, well, in my opinion, monkey patching isn't always the best thing to do, and yeah, don't shy away from using threads, really. I think despite the global interpreter lock, etc., threads sometimes are a useful tool to use, and dare to use them, really. Thank you.
Thank you for your talk. I have several questions, please. First of all, as far as I know, ZeroMQ is based on C library with its own socket code and so on. How does Eventlet work with it?
Eventlet does ZeroMQ has hooks in its. So ZeroMQ is usually runs in a separate thread, but it's a C thread, so you can't see it from in Python. And in there, it uses its own event loop, basically to do I/O just in one thread instead of having to spawn lots of them. And in that I/O loop for ZeroMQ, they provide hooks that you can hook into, and the Eventlet code for ZeroMQ basically ties into that hook and hooks up their own I/O loop into the ZeroMQ I/O loop and makes them cooperate. I haven't looked at the code exactly, but that's kind of how it works.
Thank you. Also, you said you used spawn n when you do not need a resulting greenlet, yes?
Yeah, that's right.
Why not just use spawn and ignore the result?
Yeah, good question. There's basically spawn n is slightly more efficient because the way it is implemented on the Eventlet hub, it kind of saves a little bit, so it's a bit more efficient. But yeah, if you don't do it, you're not going to be that much different.
And the last question, what happens if you don't use wait for some greenlet and an exception is risen there?
you will never know there was an exception. It's the same as if you have an exception in a thread. If you don't look out for the exception, you'll never see it. If you have so logging, there's basically no logging. It's the same. The only thing you get is if you want logging, you have to set it up yourself. So obviously it needs to be integrated in your logging thing. Eventlet can't really do anything there. If you do end up with an exception in a greenlet that was uncaught and completely rolls out and you never wait on it, you will end up getting Eventlet by default, but you can turn that off as well. But by default, you'll end up getting it on standard output, or standard error actually. So you get this traceback there. But obviously in a real application, once you're running in a standard error, it's going to be, if you demonize or something, it's going to be lost. So you have to make sure you don't end up leaving tracebacks on standard error. But the same happens with real threads if you go exception real threads. If you don't set anything up, you end up on standard error really.
I actually had a couple of questions. First one, you mentioned beware ORMs. Was that just a general race condition situation, or is it something more dangerous?
Okay, so that's kind of based on a bug report. Someone basically tried to use, because I think it was using SQL Alchemy, but because the ORM does lots of laser evaluation things, but they had to do it in a thread pool because it was because otherwise it would be blocking the main hub. But the problem was because the call that you have to pass into the different thread with the ORM contains a lot of Python code and included logging code actually, and it needed to, it was because of the lazy evaluation that the ORM does, etc. It needed to be that big block of code passed into the thread pool, yeah, which triggered the logging, which triggered the problem of the logging trying to use a lock that isn't aware of multiple threads, and that's why I got the beware of ORMs there.
Yeah, and I can see why that would be a potential problem. The second question I was having, maybe I missed this part, but could an event hub be given several different threads to play? So you could basically, you want several processes going on at the same time, but you're able to use greenlets to better divide up the usage of those in a single hub, if that makes sense.
Sorry, say that again?
Sorry.
No.
Is that being... Sorry, no, it's just literally whether a hub could manage multiple threads for dealing with so you could basically share them out to use with many more greenlets.
No, you're kind of restricted to, you can have multiple hubs, but you can only have one hub in a thread. And if you want multiple thread, you need to, you can decide not to start a hub in the second thread, but you can also start a hub in the second thread as well if you want, or any. Okay. But you can't have one hub across managing multiple threads, unfortunately.
At the bottom of the previous slide, you had a mention of G-Event. How would you compare Eventlet and G-Event?
The main difference to me is the fact that in G-Event you kind of almost, I may be corrected in this, but you're almost forced to monkey patch everything. And it's certainly when we started using it, I'm pretty sure since then G-Event allows multiple hubs as well, but certainly at the time G-Event didn't allow multiple hubs, so you were tied to one thread only. But it's the way G-Event kind of really forces you to go the monkey patching route and doesn't allow you to do the two at the same time kind of thing is the main difference to me.
One more question for me. Are there plans on enhancing interaction between common threads and green threads? For example, maybe the most interesting thing would be migrating green thread from one real thread to another.
No, you can't. The green.
I mean, on the plans for the future.
I don't know. That's basically a question you'd have to ask to the greenlet people. I'm not aware of any such plans. Possibly, I think, if that sort of thing you want to do, you might want to look at stackless Python, because they they actually have modified their interpreter. They can pickle their greenlets as well, and they do. They're more flexible in there. I don't exactly, but yeah, I'm not aware of any such plans.
So, no more questions? Okay, so that was it. I want to remember everyone about this evening event, the Pi Barbecue. And, well, thank you.